I don't even know what it feels like anymore. I'm just here and I'm trying not to die.
I can only function. I told you that I got it. I
told you that hydroponics had a freshman year. If you watch that timer, start crying, timer ended, she stopped crying and went back to work. And I was like, man, that's about all the time you have time to cry for.
Was she fairly concerned? What? Was she fairly concerned?
Oh, yeah.
All right. All right, I think we're good. A couple things. Went through, recorded the homeworks. Also posted the keys. So that the keys are available just on Blackboard. So you can, what I suggest doing is checking out, looking at the keys and looking at your homework to see how well you did. All right, see what you matched. Now, if your answers match my answers, it's a good thing. If they don't, then look to see, where your work differs from my work. All right. And if you have questions, you can always ask. So our exam is still set for Monday. I would say plan for the closed book portion in the lecture section, and then the application R stuff during the lab. So go ahead and plan for that. We haven't received the full itinerary. I'm going to guess we'll get it either later today or maybe tomorrow. So on Friday we'll know. Hopefully I'll be able to state it. All right. So this is where we left off. Standard error. All right. So we use standard error because we are trying to approximate a mean, and we want to know how good is our approximation. And the standard error gives us our measure of dispersion that we need. All right. In standard error, it is the standard deviation divided by the square root of the sample size. That's defined as our standard error. R doesn't have a built-in standard error function. There's some packages, at least one package where it is, but why load that package just for the standard error when we could write a function? So if you remember, this is where what we did yesterday. We wrote this function. We wrote that function. You should save it in your list of useful functions, right? So when we need to do standard error, we can run the chunk, and now this function is accessible. That function is accessible. So what is this list of what is this file of useful functions? Well, if I go to my drive, so I can do ASU, that's R. I have an R file. Usually it's called useful functions, but I have this R file here called function script. Function script.r. And this is just, it's not an RMD file, it's just a basic .r file, a text document that holds all of the things that I might need to know or I might use again. So I have my standard error function, and with that function, so in these scripts, the pound sign hashtag says don't run this code, just like it's in the chunk. But now from the useful function, I can just copy and paste it into my RMD file, and it's accessible. I have some other things, so I have this. So I did have, before we got the computers fixed, I had to run this in order to get the RMD files to actually create properly. But you can see I've got bootstrap confidence intervals. I have a sign test that we'll get. I have a G test for goodness of fit function that I've made. I've got a randomized g-test that I've made, a permutational correlation test, permutational ANOVA, permutational t-test. We're going to get to a lot of these in this class, and then we've got restricted permutational, two-way permutational, things that the grad level classes do. But I have this separate script that kind of holds all of these functions or all of these tests that we use on a regular basis. So you might want to do that, and that saves you from having to go back and find the notes. Find the class day where we had the notes that, oh, here's the function. You know, it might take you 5 or 10 minutes to find that. Whereas if you have a useful script file, then you just go right to there. So I've got this standard error, and we said we're going to report standard error whenever we're summarizing data or reporting data with the intention of performing some sort of statistical test. So if we measured something and our plan is to compare groups, or maybe compare time points, yeah, you should report standard error. Right. If you're only reporting a dispersion measure to be informative, like reporting on morphometrics, and you're not going to compare it to anything else or make any sort of statistical comparison, then you can report the standard deviation. That's fine. If you choose to do standard error, there's nothing wrong with it. But normally in the morphometrics world, they report standard deviations. And I give you some example write-ups on how to do that, how to report that. All right, so what about confidence limits? Confidence limits are the extension of our standard error, and we need the standard error in order to calculate the confidence limits. All right, confidence limits is another word for interval estimation. We're trying to estimate what our true value is, and by presenting a confidence limit, we're specifying that we're X% confident that the true value is going to be captured by these limits. All right, so just remember that our population size, population size, I was talking about this yesterday, but our means represent a single point value. That's what it represents, a single value. Right? If we repeat it, our sample value could be different, but the population is going to stay the same. So if our estimate's good, then our sample statistic equals the population parameter. If we're not equal, then it's a bad estimate. However, this awful claim really depends on how far away are we. How close are we to our actual true estimate? So this is where our confidence interval comes into play. The interval, or it's defined as the interval that is expected to capture the population parameter with a probability 1 minus alpha. It's the interval that's expected to capture the population parameter with a probability of 1 minus alpha. This expected to capture is important, and that's why I emphasized it with a bold. Right, and it's italics. If we work with a 95% confidence interval, our alpha is 0.05. 1 minus 0.05 gives us a 95% confidence interval. So that interval would then be, we're 95% confidence that that interval captures the population parameter. Right, so just kind of stop and think. Captures that parameter. Let's change the wording and say we're 95% confident that the population parameter is within that range. So two ways of saying it. What's the difference between those two? So option one, we're 95% confident that our population parameter falls within this interval. Option number two is we're 95% confident that our interval captures the true parameter. What's the difference between those two ways of saying it? They sound like they're the same, right? In this way, as part of our definition, we're 95% confident that the interval captures the population parameter implies that our limits could change, that our interval could change. And that's true. It can. If we take another sample, we're going to have a different mean, we're going to have a different standard error associated with it, so our interval can change. It may shift left and right, it may expand, it may contract. The other way, when we say we're 95% confident that the population parameter falls within that interval, implies that the population parameter can change. And that isn't true. Population mean is the population mean. It's a fixed value. So with our definition, know that this is the appropriate terminology. It's our intervals that can change, not the parameter. So our intervals that we have are going to be marked by upper and lower bounds. We can report it as the average plus or minus the value that gives us the full 95% confidence. Or we can actually give our limits, our lower and upper range. I actually prefer the lower and upper range because a lot of times we don't want to make the assumption that our data are symmetric, or that the interval is symmetric around a mean. And you'll see that. So here's an example. All right, we calculate the mean of 5. Right? We calculate a confidence interval, and let's say it's a 95% confidence interval, and that goes from 3 to 7. So from 3 to 7, the lower to upper bound, that's 2 units below, 2 units above. How do we interpret that? Well, we interpret it as saying we're 95% confident that this limit, this 3 to 7 limit, is going to capture the true population mean. That's our interpretation. Because it's these limits that can change, not the population mean. And that's what this entire slide is talking about. So I want you to I guarantee people will get it wrong on the exam. We'll get the interpretation wrong. Some of you will say, we're 95% confident that the mean falls within this range. No, it's not. We're 95% confident that this captures the true mean, that our sample captures that true mean. All right, so how do we calculate it? Calculate it fairly easily. It's this equation. Is there, you might ask, is there a function in R? Do we have to know this? I'm going to say no, there's no function in R. There's probably a package that gives you a function, but there's no function. So we have to do these mostly by hand. But that's not a big deal because our interval is our mean plus or minus this t value times the standard error. Well, we have a function for standard error, right? STERR. We know the function for the mean, right? The only thing we don't have is this, t. This t sub alpha n minus 1. This value represents a critical value from a t distribution. So we're going to have to pull this number from a table, or, as I'll show you in R, we'll actually use QT to figure out what that value is. So, what's a t distribution? T distribution is a continuous distribution. Hopefully you can guess that this is non-normal, right? Since it has its own distribution and it's not called normal distribution. So what I want you to recall is that the mean minus mu over sigma, we were doing that in the normal probability. If we apply this transformation to all of our data, x minus mu over sigma, then our data will now, or the transformed data, will approximate a normal 0-1 distribution. Right? But we have to know the population mean, we have to know the population standard deviation. We normally don't know those values. So what we do is we approximate the population using our sample average, but then we approximate our standard deviation, the population standard deviation, using our standard error. The standard error of the mean, which is approximation for our population. So that's that s over the square root of n. So it's a similar type of transformation. However, because we're using standard error at this point, we no longer follow a normal 0-1 distribution. Instead, what we follow is a t distribution. A t distribution is defined by its degrees of freedom. The degrees of freedom for our distribution is our population size minus 1. All right, it's basically this value minus 1. So since our t-distribution is defined by degrees of freedom, we have an infinite number of curves that we can get. We can have an infinite number of curves. Fortunately, though, as we approach large sample sizes, our normal curve starts to become more and more like a normal curve. All right, so how different are they? Well, these are our graphs. So we've got black is our normal curve. All right, red is 1 degree of freedom. Blue is 5 degrees of freedom. So our normal t-distribution is that we have fewer points in our central and shoulders and more points in our tails. We're like tail heavy for the t-distribution. But as our sample size increases more and more, we get pretty darn close to a normal distribution. So close that we actually use a normal distribution to approximate. So who came up with this? This was developed by W.S. Gossett of the Guinness Brewery. Beer, it's everywhere. All right, it's everywhere. He called it students' t-distribution. Why? Because there was regulations on what he could disseminate in terms of information. So all of his statistics work, Guinness owned it. So instead of publishing under his name, W.S. Gossett, he published under a pseudonym called A. Student. So initial A and then student as his last name, and thus students t-distribution. So hopefully no one said, well, this is t-distribution because all our students use it. No, it's not correct. It's not why it was called students t-distribution. It was named for his pseudonym. All right. What do we know about the t-distribution? It's symmetric, just like the normal curve, which is nice. If we go to a point above, so if we go to 1 and we look at the area to the right of 1, that's the same area as to the left of negative 1. It's great. Limits, negative infinity to positive infinity. But in reality, once we get up to 3 or more, or plus or minus 3, and beyond, value is basically 0, really small. And then the shape depends on the degrees of freedom. Shape is the degrees of freedom. It's the degrees of freedom that we're going to use as our sample size minus 1. Just memorize it. Why is it minus 1? Because we made an approximation. We estimated our population mu using our sample. And because we made that estimation, we lose a degree of freedom. And we'll see this loss of degree of freedom again. So incidentally, this n-1 is the same n-1 that's used in the standard deviation equation. So that's our t-distribution. How do we get it? I'm going to go to Blackboard real quick and open up our t-distributions. All right. Biometry. So in our statistical tables folder, I have a t-table. And they all look the same. They all basically look the same. Like this. I like this table because it shows you the area under the curve that is being reported in the table itself. So this is reporting our tails. And it's reporting 2 tails. All right, so how do we use it? We use it by, open this up just a little bit, looking at our alpha level. Our alpha level is basically a type 1 error. That's our alpha, and that's why our confidence said 1 minus alpha. So if we wanted a 95% confidence interval, in order to get 95%, it's 1 minus 0.05. This 0.05 represents 5% in both of our tails. 5% in the upper tail or I'm sorry, 2.5% in the upper tail, 2.5% in the bottom tail. So the total, the sum, represents 5%. If we wanted a 99% confidence interval, we go to this 0.01, which is 1% in our tails. So it's 1% total, which means we have 0.5% in the upper tail, 0.5% in the lower tail. So we go to whatever alpha we need. For our t-test, we set our alpha at 0.05. For our confidence intervals, it depends on what confidence interval we're looking for. The typical one is 95%, but we could also do 99%, we could do 90% if we wanted to. So we go to our appropriate confidence interval, and then we read down the table. Each of the rows represents a different degree of freedom. So here our the V, the V here, represents degrees of freedom. So if we had a sample size of 10, and we're looking for a confidence interval, a 95% confidence interval, we're going to read down this 0.05 column. And our sample size is 10, so our degrees of freedom is actually 10 minus 1, which gives us 9. So we would use this 2.262 value as that T critical value in our confidence interval. All right?
Wait, repeat that one more time. I need that
95% confidence interval. All right, we're going to read down that 0.05 column, and we have a sample of 10. 10 of these beetles that we measured. All right? Yep, so our degrees of freedom that we use is 9. 10 roaches minus 1, or 10 beetles minus 1 is 9. That's our degrees of freedom. So we're reading to the 9th row. This is the value that we use for our T critical.
Do we need to print that out?
Yeah, we'll probably do that. We'll do that. All right. So what we're gonna do, yeah, and then like for exams, I'll have some extra copies, or I could always print some more. So before we get to the QT, all right, here's some examples. So what I want you to do is just find our T critical, because that's what we're going to use, our T value that is used for a 95% confidence interval, using our table. And what I'm going to do while this is going on, I'm going to add it to the markdown, to my markdown document. Pull those values from the table. So I'm going to start doing this, because what we'll do is we'll confirm it using R. So if we're doing these things by hand, we need to know what our T value is. And we can use a table to do this. So we're dealing with 95% confidence interval, 12 degrees of freedom. So with 95% confidence interval, we use the 0.05 column. We read down to 12 because that is our degrees of freedom, and it says df equals 12. So our critical value for this one is 2.179. And I specify t crit. That's our cutoff. So basically, this is the value where we have 5% in our tails. 99% confidence interval. That means our alpha is 1%, so 0.01 column. I read down to 18, which is the DF value. I give the DF, and I get 2.878. 90% confidence interval. Alpha is 0.1. So I'm going to go to the 0.1 column, and I give you sample size of 10. I give n equals 10. We don't use the n, we use degrees of freedom. Our degrees of freedom is our sample size minus 1, so I go to 9 degrees of freedom. And with 9 degrees of freedom, I get 1.833. All right, so note n equals 10, but degrees of freedom equals 9. So that's the one that I used. And I just used the table. So yeah, we've got the normal table, kind of have to demonstrate you can read it. T-table, you have to demonstrate that you can read the T-table. And we do that because if you encounter problems like these, unlike the MCAT or the field test, major field test, you're not going to be given R to calculate this in the computer. It'll give you a portion of the table, or it'll give you a table that looks something like this. Or it may only give you a single column, and then you had to figure out what the degrees of freedom, which one to use. And remember, degrees of freedom is our sample size minus 1. Can we do this in R? Yep. So we can confirm our t-crit values using R. The function is qt alpha df. Let's confirm that. Let's go back to here. All right. And whoops. Let me go back here. We have a lower dot tail that we can add. All right, because what this is, the actual function, or what I give you is Q, which is a quantiles. And that's what our table gave. That's at the top, the alpha. Those are the quantiles. We're trying to figure out what value goes up to that quantile. So the 0.05 table, or that 0.05 column, when we get to this value, let's use that 9, 2.262. Negative 2.262 represents the 5 percentile. So 5% of the points lie to the left of that. If we continue going up to the positive 2.262, now we capture, actually no, this isn't 5%, this is 2.5%. 2.5% is at this level. And then if we go up higher, once we get to that upper value, now we have 2.5% to the right of that for a total of 95%. I just prefer using the alpha level, all right, to specifying the alpha. Makes it a little bit easier. And then we could say lower dot tail equals T or lower dot tail equals F. So alpha is the alpha level, or is the percentile, the quantile. DF is degrees of freedom, where again DF equals n minus 1 for our confidence intervals anyways. And then lower dot tail is equals T if we want the lower quantile, equals F if we want the upper quantiles. So kind of the reverse. All right. So we're looking for a T critical value. We want a 95% confidence interval. So what's alpha? Five percent, right? Right? 5% is the alpha. So if I do 0.05 and I do df equals 12, right? I'm going to leave lower dot tail equals t. This is what I get. So, a couple of things. So for our first example, let's try this. Observations. Number one, the value is negative. Why? Why is it negative?
Looking at the lower tail.
This is the lower tail, right? T distribution goes from negative infinity to positive infinity. All right. And we're looking at that lower tail. So we should get a negative value. All right. Second answer, or second observation, the answer doesn't match the answer from the table. All right, so the question then is why? Why doesn't it? No, it is. It's equal.
Okay.
It's part. Yeah, our T distribution is symmetric. It's centered at 0. So yeah, we're equal on both sides. But like we came up with the T critical in this table of 2.179. This one came up as 1.78. We'll ignore the negative. Let's go to the table. We had 12 degrees of freedom. We should have had this, 2.179. Look at what we got. We got this one. This is the 0.1 column. So where did we go wrong?
It's taking 5% away from both sides, right?
Yep, so we use 5%. Alpha equals 5%, which says 5% of the points to the left of our distribution. But we want 5% in both tails, 5% total, or we want a total, I should say, we want a total of 5% in both tails, which means we want 2.5% in the lower and 2.5% in the upper. So that's going to change what we put up here. So the correct method that we need to use is something more like this. QT I'm going to make a vector because I'm going to ask for two different values because we want the lower and the upper, and we could always just ask for one, but it's usually better to do the upper and the lower. So I'm going to do 0.025 and 0.975. I'm going to ask for the cutoffs for both the 2.5% and the 97.5%. How many points, what percentage of points are above this? Yeah, 2.5%. So we've got 2.5% to the left, we'll have 2.5% to the right, or the equivalent would be 97.5% to the left. We're going to do degrees of freedom equals 12. All right, and I'm not even going to write the lower dot tail because the default is t, and that's what I want. I've written my formula, my function, to give me the correct answers. And when I do, you'll see I get two. I get a negative and I get a positive. So, why do we ask for both the 2.5 and the 97.5 values? Any ideas?
And that equals 5% total, right?
Yep. %5 total in the tails, and 95% in the center part of the distribution. There's another thing, though. We can pass this function directly to our 1 minus alpha percent CI equation and get both the upper and lower limits. And that's good because R doesn't offer plus minus signage. It doesn't give we can't do plus minus and have R automatically do that. But we can do it here because these are the same values, 2.1788. It's just we have one that's positive, one that's negative. So if we write our confidence interval equation where it's the mean of a vector plus our QT value times the standard error of that vector, R is going to return the lower value, so that's negative, and it's going to return our upper value with our positive. So there's a reason why we do this. So this was for the first example, 95% confidence interval, DF equals 12. And we had a t-crit of 2.179, which is this, just rounded. So now, use the QT function to do these other two and confirm that we do get it. And remember, we kind of have to think, it's not just the alpha equals 1. We have to kind of figure out what percentage is in each tail and use those numbers in our QT function. All right. We're going to look for those. Have those. That's what we're asking for. Yeah.
A different.
Yep. So did I use the actual like percentages? 0.5%, 95.5%. How did I write those?
Oh, okay.
Should be the same value. So one of those is off. So we should get the same value, plus and just a plus and one's a minus.
Oh, I know what it is. Yep. Okay.
So I think if anything, the hardest part is just trying to figure out what values do we use. So for that first one, it was a 99%. So we need 1% total, or 0.5% in each tail. So I can use the 0.005 for one, and then 0.995 for the second. And we got DF18, and again, these are the same values, it's just plus or minus. For the 90% confidence interval, that's 10% in our tails, or 5% in each. And that's how I would write it. Yeah, you're going to have to be able to do this at different confidence intervals. Yeah, it's just kind of a check. You might have one, maybe two. And we'll have a check just to make sure you can do it. But then, after we do that check, basically all of the confidence intervals that we use is 95%. So, the one that you should just kind of drill into your head is this. That's kind of how we do it. All right. So, what we're going to do is we're going to pick this up on Friday to go through the confidence interval of the mean. We're going to talk about the confidence interval of the mean, and we'll kind of wrap up. So, being able to calculate the confidence interval of the mean, that'll be on our exam and the definition of a confidence interval. But as we'll look ahead and we'll look forward, we're going to do bootstrapping, because a lot of times our data are not normal. And why produce symmetric data if we're skewed, if the underlying data or why produce symmetric intervals if our data are skewed? All right. I won't ask you to do these by hand. We'll use R for the confidence intervals. All right. All right. Call that a day.